Okay, so this is for chapter 4 in your test. Chapter 4 is one question, chapter 5 one question. So chapter 4 basically will carry lebih kurang 20 to 25 marks lah in your test tu. Okay, and our chapter 4 is basically will be covered for time response of a control system. Initially in chapter 1, 2 and 3 you already develop a system kan. You have a system with the mathematical modeling, you have the transfer function, also you know the representations of the system in terms of block diagram and also the signal flow graph. Okay, for this chapter 4 we will evaluate on the performance of the system, accuracy dia lah. Okay, for our system, error dia tinggi ke rendah ke and so on. Okay, and as introduction here, this chapter will studies on how the system of for the output changes over the time lah. Okay, with time after in the input applied, meaning that we have a equilibrium system. Okay, at t equals to 0. Let's say kalau kita ada one motor at t equals to 0, kita tak startkan lagi, so the motor is not moving, not running. And then when we put an action, kita onkan dia, we put again kat situ and so on, and then the system will start. Tapi sometimes when we have a system, initially dia akan fluctuate dulu. Sekejap lagi we will see on the graph, and to become a stable there ada certain period of time. Okay, so itu yang kita akan study in this chapter 4. Okay, so we will have two types of time response of a control system, two parts. The first is the transient response. Okay, the transient response, this one, from initial state to the final state. For example, if we have satu system, so this is the characteristic characteristic of the system itself. Okay, so this is the first part adalah initial part yang ni, this one. Okay, masa dia nak start naik tu. Okay, it is not stable yet. Okay, in active region. So the second part will be when the system become stable, yang ini, yang belakang tu. Okay, so number 1 is the green area, number 1. Number 2 is the blue area. Okay, number 1 is temporary response immediately after the input is applied, or we can say that exists before the system become stable. Okay, how we can determine the system is stable or not is dekat belakang ni. When the output is straight line, maksudnya achieve desired output. Kalau kita set yang bawah is the time, x-axis is the time, okay, y-axis is the magnitude, magnitude lah. Okay, kalau kita set the time is infinity, impossible lah pula our system nak infinity kan. So might be lots longer period of time, so the system dia tak akan fluctuate dah. Okay, due to the stable condition. Okay, and for example when we have oscillations ataupun overshoot, rise period, so that one kita call as the transient response. The second part here we have the steady state response. Steady state response meaning that the final behavior after a long time, meaning that kita dah set kat sini the transient response TR, and then steady state yang belakang when we achieve the stability. Okay, so this is the final behavior when the system become stable. Okay, as you guys can see kat bawah here is the system response with both of the response. CTR is the transient response. Okay, CSS is the steady state response. This one CT is the total response, overall output of the system with respect to time. Okay, and CTR is the transient response, temporary part of the response, meaning that dia belum final lagi, dia tengah nak on. Okay, untuk capai the optimum conditions. CSS is the optimum output, steady state response when when we set t equals to infinity, we still can get the output juga. Okay, dia tak akan kacau dah. It is stable, constant or predictable, and then remains after a long period of time. Dia tak akan berubah dah. Okay, so kat mana when we have the disturbance, kat mana we need to set the gain ke apa ke, kat sini lah. Okay, kat sini yang penting. Okay, sebelum kita capai the stability. Alright. Contohnya kalau kita ada motor speed, okay, sebelum you start motor, contohnya kita dah set nak 60 revolution per minute kan. So when we set nak capai 60 tu, dia akan naik dulu from 0, 20, 30, 40 sampai ke 60. So from 0 to 60 tu is the TR, transient response. And then the 60, bila kita dah set 60 contohnya, dia akan duduk dekat steady state. Okay, so that is the transient response and steady state response. Normally a system mesti kena ada these two parts, transient and steady state. Okay, alright, so now kita tengok on the first order. Kat sini still kita akan tengok first order and second order dari chapter 2, 3 and 4, 5 pun still we are still dealing with the first order and second order. Okay, for the first order it is a good control system should have. Macam mana kita nak tahu good control system? Mesti ada fast transient response. Maksudnya yang transient response tu yang ni, this part kan, transient response. So if it is fast transient response, maksudnya dia akan naik dengan cepat. Yang ni dia macam slow sikit, naik dengan cepat. Mungkin dia suka pen. Macam tu. Dia nak become stable, dia lebih cepat sharp dia. Okay, so that is fast transient response. Kalau lagi lambat, dia lagi landai lah. Alamak, dia jadi gambar pula. Dia jadi ke belakang lagi. Okay, so that is lagi slow transient response. Tapi we must be very careful when we want to design. Kalau kita set transient response ataupun gain dia terlalu tinggi, mungkin dia akan fluctuate dulu, dia overshoot. Sekejap lagi kita tengok graph for the overshoot. And also overshoot, kalau we have larger overshoot, the system also it is not stable. Okay, overshoot tu maksudnya kalau let's say if we have a system, okay, overshoot tu kat mana? Overshoot tu kat sini. Okay, sepatutnya kita nak macam ni je kan. Overshoot tu dia tersalah shoot dulu. Sometimes overshoot ni occur due to kita when we design kan, kita ada transfer function tu, might be kita letak dia punya value gain tu, yang atas 1 ni adalah dia punya gain. Gain tu kita tersalah set. So it might be too fast response, terlalu cepat, so dia akan overshoot dulu. Okay, so that one kita boleh kira semua, the overshoot, maximum overshoot, the rise time, peak time, semua we can calculate. Nanti kita akan tengok on the formula. And also short settling time. Short settling time contohnya kalau macam ni. Okay, yang bawah is the larger settling time. Okay, sebab dia nak settle dapat dekat output tu lambat. Okay, and also accurate steady state response, meaning that when we have higher accuracy, lower error. Okay, same concept as you learned in numerical method kan, you kira the error. If we have lower error, accuracy will be very high. Okay, so this is representations of the block diagram. We have the first order, A is the first order, and then B is the simplified without the gain. This is unity gain. So this one macam mana nak dapat? With the when we solve G over 1 plus GH tu lah. So you can get this one. Yang atas here like I mentioned earlier, this one is a gain value. Okay, macam ni lah. This is a gain value, a constant number. Okay, so macam mana kita nak tukar performance of our system? By designing the value of the K. Kita boleh vary the value, naikkan ke, kecilkan ke, okay, on the value itself. Alright, so for the system also kita akan ada 3 types of response: unit step, unit ramp and unit impulse. So what is the difference between these 3? Unit step is kalau bila you ada macam digital discrete kan, macam tangga tu, okay, 0 and 1 like so on. So that is unit step. For unit step it is 1 over S. Kat sini pun ada. Unit ramp is bila kita ada slope, when it is in slope value. So kalau slope 1 over S square. And unit impulse is bila kita ada only a magnitude on a certain period of time sahaja, pada satu masa je. So that is for unit impulse. Okay, for unit impulse, RS input dia adalah 1, satu value. Kalau dia kata unit impulse is 5, meaning that it is 5 lah. Okay, kalau unit step tadi, kalau 5 over S. Itu beza dia. Alright, so this one is the first for unit step. Okay, unit step, how to set. Kalau dia kata it is content unit step input, so you akan letak darab dengan 1 over S. If it is unit impulse, darab dengan 1. If it is unit ramp, 1 over S square. Okay, so this one, how to get yang ini is inilah. Yang ni sebenarnya kita solve by using partial fraction, baru you boleh dapat yang ini. Okay, and then yang bawah here is taking Laplace. That is why for chapter 4 we are still dealing with the Laplace table. Okay, nanti in test you will get the Laplace table as well. Okay, this is one example to relate with the transfer function. Sama je with chapter 2 yang kita belajar hari tu. Okay, when we have a spring and a damper, so this one is sama like you belajar earlier. And then this one is from the transfer, the Laplace table, you boleh dapat this one. And kat sini dia masukkan S yang ini. Okay, so taking partial Laplace, dia akan duduk yang ni lah. Initial kita tak ada 1 over S, and then kat sini when we have a unit step input, so you akan ada 1 over S. I think dalam soalan test hari tu pun ada juga kan, unit step yang 1B, saya rasa ada. Okay, tapi ramai pula yang tak boleh jawab soalan yang spring tu. Yang boleh jawab boleh lah, yang tak boleh jawab pun ramai juga. Okay, alright, so saya nak fokus on this one sebenarnya untuk chapter 4, sebab yang ini you guys dah tengok dah sebelum ni, lebih kurang je. So I want to focus on this one. This is a system. Let's say we have this blue and red system. Which one is better? Kenapa? Because dia rise time dia lebih cepat, and then dia lagi cepat steady. Actually tu untuk kita cut adalah dekat 63.2%. Okay, so at 63.2, masa yang dia ambil for this red mungkin kat sini mungkin 30 ataupun 40 kan. Untuk blue 100 lebih sikit kan, betul tak? Okay, to achieve the 63% ni. Okay, so this is comparison when we set the gain berbeza, when we set different gain, so kita akan dapat that one. So yang ini kita panggil as rise time, TS. Okay, and yang ini tak nampak dia punya peak time. Sekejap lagi kita tengok yang we have the overshoot, that one boleh nampak dia punya peak time. Okay, rise time, and kat sinilah yang 62% tu one cycle. Actually the 62 is for one cycle tu yang kita boleh dapat this value ataupun yang ini. Okay, and yang this is bila become stable, yang tu lah might be kalau if we have another system pula, bila kita tukar dia punya transfer function, mungkin dia akan jadi macam ni. Yang warna hijau tu it is dia stable juga, cuma dia lambat nak become stable. Rise time dia sangat lambat. And another one system yang mungkin boleh ada is yang warna hitam. Yes, dia naik dulu, dia shoot terlebih, ambil lajak lebih sangat. So this one kita panggil as overshoot. Okay, overshoot tu dia terlebih daripada yang sepatutnya lah. And then dia oscillate sikit. At this point dia oscillate sikit, lepas tu baru dia become stable. Okay, so at the end dia tetap akan achieve stability juga, cuma at the early stage tu je dia oscillate dulu. Okay, and by default sebenarnya in practical that is the most general ataupun yang paling biasa kita jumpa for a system. Okay, dia akan fluctuate sikit baru dia akan stable. Same goes kalau contohnya if you want to on a generator, dia akan gegar dulu lama sikit baru dia akan constant. Okay, so that is the overshoot lah. Alright, so this is a calculations how to get on the 63%, to get on the peak time tu. Okay, so for this one we are considering on the, this one is for first order, applying for unit step, so darab kat sini, and then this one taking Laplace, ini partial fraction dulu, lepas tu baru Laplace inverse Laplace lah. Okay, and then when we solve, masukkan the value of the t equals to tau, then you will get this value. This one t equals to tau, then we can get this value. Okay, ini yang tadi. So basically for this is the time for TS root T, TS rise time. Okay, as the time increases, the arrow approaches infinity, dia yang ni lah become stable. Okay, ni lebih kurang tadi. Alright, so when we have this one is unit ramp, kalau tadi 1 over S unit step, this one is unit ramp unit step 1 over S. So kat sini kita masukkan 1 over S. For unit ramp kita masukkan 1 over S square, and then taking a partial fraction, you will get this one, and this is inverse Laplace. Okay, inverse Laplace we can get this one for unit ramp. And unit, kalau for unit step tadi we can get the graph macam tu kan. Okay, for unit ramp it is terbalik sikit, like this. Okay, so this one for unit ramp punya graph. Okay, as t approaches infinity, the arrow signal approaches to t. Okay, larger time constant causes the larger lag in between. Okay, the last one is unit impulse. Unit impulse kita masukkan the input is S1, so maksudnya dia darab dengan 1. That is how we can get this one saja, and taking Laplace you can get as this one. Unit impulse, the graph dia. Okay, so this is the graph how to get the unit impulse. Okay, impulse response graph for this one, the output suddenly rises for decay exponential, eventually decreasing, and then bila kita time approaching infinity dia akan become 0. Okay, that is why among all these 3 units yang biasanya kita akan pakai adalah unit apa? Unit step yang ni. Okay, sebab senang we want to observe on the output. Okay, alright. So now there the relationship in between all the inputs, either unit ramp, unit step, or unit impulse. Okay, when we take derivative of unit ramp, yang ini, dc over dt, we can get this one. When we take derivative of this one pula, we can get yang ini. Betul tak? So yang ini derivative dia boleh dapat as this one, yang ni, and then derive yang ni pula, you can dapat yang ini. Differentiate lah. Differentiate you can get. Okay, ramp derivative dia give step, step derivative give impulse. Okay, and impulse response can be obtained from the step response differentiations. It is very important for this one in signal and also for the control theory, meaning that when we want to control the whole system. Okay, ada soalan tak setakat ni? Am I too fast? Ha? Sulang kat mana?
Section 7, SMK section 7 tapi sedia habis nak kat kedua.
Haish. Okay, duduk. Alright. Okay. So now kita nak pergi to important part. Okay, kalau tanya saya for chapter 4, yang ini yang paling penting. Okay, and dalam soalan memang yang ini tak akan lari lah, memang akan ditanya about this one. Okay, so for this equation, this is the standard format for second order transfer function. Okay, so in here apa yang you tak pernah nampak ke dah tahu dah? Wn omega n dengan zeta value. Okay, the omega n is kat sini you baca natural frequency. Okay, omega n equals to 2 pi f n. Frequency. Since it is frequency, the kita panggil apa ya? Units. The unit is radian per second. Okay. And then damping ratio. The other one is damping ratio. Damping ratio. It is dia macam bentuk cacing sikit tu. Okay, the symbol dia. And this one, there is no unit for damping ratio. Kenapa? Tak ada unit. It is ratio. So that is why there is no unit about this. So these two components adalah very important untuk we determine the damping of the system yang kita ada. That is why ini adalah antara benda yang kena kira lah. Okay, natural frequency and damping ratio. Natural frequency is the frequency for every, dia bukan every benda hidup, every existing benda ataupun existing system lah, from equilibrium nak capai the stability. Okay, so that is the natural frequency. Okay, so we can have 4 cases of the damping ikut pada value yang kita kira lah. Okay, what are the cases? The first one, marginally stable. Alamak, tak nampak pula. The first one is marginally stable. Okay, the poles duduk dekat axis. So, the value for the zeta is equals to 0. When you calculate, mesti dapat 0. Okay, and the graph will be like this. X-axis is the time versus this one kita panggil as magnitude lah. Okay, oscillate continuously sampai t equals to infinity pun the graph will be like that. Dia akan continue to oscillate. Okay, for this one. This is the first condition. Okay, the second condition, case 2 is under damped. For under damped, value for the zeta or poles is in between 0 to 1. Dia duduk kat situ. Okay, under damped. And the graph will be like this. The shoot, overshoot, lepas tu baru stable. So this is the graph for under damped case 2. Okay, ada 4 case. Ni bukan case mahkamah. Case 3, critically damped when the zeta or damping ratio is equals to 1. Dia duduk situ je. Okay, and the graph will be like this. Naik terus stable. So this one is critically damped. Last one is overdamped. Overdamped is when we have the value of the poles more than 1. Zeta value more than 1. Poles dia location dekat sini. And the graph will be, dia naik, dia lebih kurang with the critically damped. Apa beza dia? What is the difference? Dia still akan stable juga ujung tu. Lambat, dia a slow response. Mungkin dia macam ni pun ya juga. Tapi somehow bila T approaching infinity, dia akan dapatlah output yang nak tu, tapi lambat as compared to critically damped. Okay, so among all these four, yang normally yang ketiga adalah ideal condition, kan? Very ideal. Dia tak ada overshoot, dia tak ada oscillate, dia terus dapat the output. Okay, but in real life, practical, normally kita akan dapat case 2 dulu. Okay, this is the initial case 2. Lepas tu when we tune our model, barulah you boleh dapat yang cantik punya. Okay, so this is the 4 conditions for related with damping ratio. Okay, this is the kita panggil apa comparison. Okay, comparison between all these 4 conditions. Okay, the first case 1 is T zeta equals to 0. Yang ni. Okay, graph dia is the black one, yang ni. Okay, continue to oscillate and no energy losses for this one. T approaching infinity, still the same graph juga. Okay, so this is very unwanted condition. Kita tak nak pun this one. Okay, because sampai bila-bila pun we still cannot get the output. Okay, and second case, yang mana second case? Second case, T in between 0 to 1. Hijau, biru, merah and orange, kan? Okay, so dia akan shoot dulu, lepas tu baru turun, baru stable. Yang orange, actually orange ni dia ada shoot juga tau, sebab dia naik sikit daripada 1. Nampak tak? Kat sini dia lebih sikit. So this one is also kita panggil as under damp. Dia ada shoot juga kat situ. Okay, for 0.7. Alright, so that is for second case. Case ketiga apa? Case ketiga yang mana satu? Warna apa? Case ketiga yang ni, graph dia naik terus. Okay, so that is the third case. Okay, fastest response without oscillation. Alright, so that is the third case. The final one is yang warna apa tu? Navy blue Okay, the navy blue. Dia tak semestinya 2 lah, greater than 1. 1.1, 1.2 pun still sama. Okay, so this is the last one. Ini yang paling kita, tak adalah paling kita tak nak. Kalau boleh kita nak elak jugalah. Okay, as compared between all this damping ratio value, kat sini ada ayat dia ni. Zeta equals to 7, give the best, give the best response. Sebab kita nak dapat yang critically damped, yang macam very ideal tu agak susah. So kita normally kita akan dapat overshoot sikit, lepas tu baru dia akan stable. Okay, so that is why yang ni 0.7 tu is the best. Yang warna orange, yang ni lah, dia naik sikit. Dia naik kat sini ni. This is line sikit je ni, kat situ. Okay, so that is for overshoot dia. So very small overshoot. We can reduce the overshoot by our transfer function, value gain yang kita letak, ataupun peak time, rise time yang kita masukkan lah. Okay. Siapa yang lari tadi? Alright, so we have one example kat sini. And then from here also we can damping ratio small, more oscillation, kan? Betul tak? Okay. Damping ratio large, less, no oscillation. Tapi no oscillation, high T peak time, no rise time lah. TR, high TR, rise time. Dia maksudnya dia nak rise sampai dekat output tu lambat. Okay, high TR. Alright, so that is why in engineering practice zeta is equals to 7. 0.7 is the best. Kat bawah ni ada lagi ayat-ayat je, you guys boleh baca lah. Consider critically damped and so on. Okay, we have one example kat sini. This one is when we have a system, sama macam kita punya test tadi tu, we have a mass, we have a spring, we have a damper. So this one is the transfer function dia. Yang ni. Okay, for this one normally kita set K equals to 1 lah, yang ini ni. Okay, okay, so this is second order transfer function. Kenapa boleh tahu second order? Sebab ada S kuasa 2. So that is second order. Okay, and in here we have mass for the inertia of system, we have K for the spring stiffness, KD is for damping strength, damper, and then omega n. Benda baru yang tadi yang ni lah. Okay, sini this one we have the omega n natural frequency. Okay, so macam mana kita nak solve soalan dia? Dia suruh kira apa? The question nak natural frequency omega n and also on the damping ratio. Lepas tu sketch. Okay, so yang ini is fixed. Yang formula with the omega n is the fixed. This is fixed. Okay, so you need to compare je. Very simple. Just compare the value, kan? So omega n masukkan je lah kat sini. Compare, ambil yang omega n. Yeah, so omega n yang ni, so you just ambil this one. Masukkan the value. Dalam soalan tadi dia bagi siap-siap. Normally kalau question like this, dia bagi siap-siap dah. Value untuk K, M, KD, all the gains tu dia akan bagi siap-siap. So you just compare, masukkan, and then you can get the first one, omega n. And remember unit untuk frequency radian per second. Okay, kita normally kita tak compare yang atas tau. Kenapa kita tak ambil yang saya bulat warna merah dengan yang ni? Because kalau when we are dealing with transfer function, kita tengok yang bawah, betul tak? Masa you buat question chapter tu, kita tengok yang bawah juga. Untuk cari partial fractions, kita guna yang denominator dia, pembawah dia. Okay, that is why kita guna yang bawah ni. Alright, so the first one is omega n. Sepatutnya tak ada masalah lah, because you just compare sahaja. Ada calculator, confirm boleh buat. Okay, and then nak cari dia punya zeta, damping ratio value. Okay, you compare yang tengah ni pula. Okay, with this one. Sebab yang ini dia ada S, so kita tak ambil lah S tu. So you tak ambil S tu, and then you compare this one. Remember for the damping there is no unit, so tak perlu letak unit apa-apa. Okay, dah kira, dapat value dia. Now kita kena make decision. Kan ada berapa case tadi? We have 4 case. Lepas tu kita kena determine lah, this damping ratio value jatuh dekat case yang mana. Okay, so all the 4 cases tadi tu memang kena ingat. Okay. In test 2 later on, we will give you Laplace table, but not this. Semua formula kita tak beri, semua case pun tak beri. Tak payah saya sedih ganyan-ganyan mata. Okay, so kena ingat ada 4 case, kena ingatlah what is the value semua. So once dah dapat the value, soalan yang last kali dia suruh sketch. So just lukis je. Tapi kita tak tahu this value pun sebenarnya. So on this axis you tak perlu letak lah dia punya ni pun tak apa. As long as when we are looking at the graph, kita tahu this is case 1 or case 2, case 3, case 4. Mana satu. Okay. Ideally when we increase value gain K, kita akan increase natural frequency omega n, meaning that it will be faster oscillation. And other than that, bila kita increase value KD kat mana position dia yang KD position dia kat tengah, so dia akan effect with the damping ratio. KD is this one. Okay, it will effect with the increased value of the damping ratio, and also can reduce on the oscillation. Okay, when we increase on the mass pula, the mass value of M tu, nama mana pen. Okay, the M, it will slow the system response with lower natural frequency. Okay, that is the relationship dia lah in between. Okay, semua dapat tak lukis this one? Very simple. Okay, kalau dah, we have 2 exercise kat sini. Exercise 1 and 2. Okay, yang kedua ni saya nak minta tukar 33 jadikan 98. Okay, cuba buat. Get me the, benda buat yang sama macam tadi. Get me the natural frequency and damping ratio. Ni pun sama, natural frequency and damping ratio juga. Kenapa ramai tak datang ni? Akhir pergi mana Aidil? Haikal? Tun Haikal? Wan belum sign. Yang nak balik awal siapa Berapa dah? Okay, sikit lagi. Okay, cuba kira. Compare, lepas tu masukkan dalam komputer. Kita nak ambil dah mati. Kalau yang dapat rendah tu dia dah sangat pula. Test 1. Kalau yang paling tinggi setakat ni saya jumpa 30 something. Yang rendah belas-belas lah. 50. Kita over 50. Tapi dia akan, weightage dia is 20, so you darab 0.2 lah kan. Okay. So for those yang nanti bila dapat, next week kot saya boleh return. For those yang dapat, kalau rendah kena come back untuk test 2. Because actually test 2 kita ada, we will cover only 2 chapter 4 and chapter 5 only for test 2. Okay, dapat tak? Yang the first one, omega m berapa? Soalnya 2K omega n. Pak Izin. Satu saya kata, the formula kita tak akan bagi. Yang ni memang you kena hafal lah. Dia senang tapi dia macam kena hafal. This one kita tak akan beri. Okay, so you need to memorize lah that one. 34 point berapa Mai? 34 point 64 radian per second. Jangan lupa tulis the unit. Lepas tu damping 1.1 15. Case apa? Case over then macam mana graf dia? Lepas tu naik, lepas tu ada shoot tak? Naik slow tapi tak adalah slow sangat, dia biasa kan. Oh, dia naik slow sikit kan, macam tu Okay, over boleh lah. Okay, so nanti kalau you sketch letaklah sini T, sini amplitude ataupun magnitude. Okay, macam tu je lah. Alright, the second one. Compare with the formula. KD dia change to 98. Sebab kalau KD dia 33, dia sama dengan yang example tadi. Sekarang Ain dapat tak? What is omega n? 16.33. Damping 1 point. Okay. Okay, maksudnya case apa? This is case 2. Yang ini case 3. Critical kan? Critically damped. So bila you lukis antara case 2 dengan case 3, jangan sama pula. Yang tadi case 2 ke? Under 1.15. Tadi case 4 lah. Sorry, case 4 kan. This one is under damped. Okay, and then for this one, bila nak lukis nanti jangan sama pula dengan yang atas. So bila lukis dia kena lebih cepat sikit lah. Okay, so this is critically damped. Betul tak? Okay, rise time dia tak akan sama. So kat sini. So here is the rise time TR. Yang ini TR dia lebih pendek lah, lebih cepat. Okay, letaklah T, letak with the amplitude. Walaupun kita tak letak unit, you letak macam ni pun dah okay. Alright, so this is the comparison. Meaning that when we change the value of KD, kita tukar value of the mass, kita akan dapat different damping ratio. Okay. Right, ada soalan tak? Tak ada?